All right. Welcome, everyone. We got quite a few here. Okay. Should I get started? Okay. Welcome, everyone, to this ETM SVIC seminar that we've been hosting for a few weeks now on Fridays. It's my pleasure to introduce David Yang, who is going to give us a talk today about his work and how it falls into this census to decisions pipeline. David is currently a postdoc at Lehigh University, but the good thing is he's actually going to join us in the Department of Civil Engineering. We're super excited to have him join us. He's going to bring a lot of really cool, great expertise to the program, and not only to the department, but as you will see, I'm sure that he will be able to add a lot of new things to the college and even beyond that. So I'm excited for David's talk. I'll let you do that now. And after his talk, we'll have some time for some questions. So David, please.
Thank you, Thomas. Thank you very much for the introduction. Hi, everyone. My name is David Yang. I'm, as Thomas said, currently a postdoc at Lehigh University, Pennsylvania. I will be joining PSU this fall at the Department of Civil and Environmental Engineering. Today, I'm very glad to have this opportunity to share some of my thoughts on census to decisions. Specifically, I want to talk about value of information gathered from different sensing technologies and how can we use this information for optimum decision-making for aging civil infrastructure. To give you a bigger picture here, the motivation of my research is basically the huge amount of old and deficient structures here in the US. Based on the latest report card by the American Society of Civil Engineers, the overall grade for civil infrastructure is D+, and for bridges, which is my research focus, the rating is slightly better at C+. And 4 in 10 bridges in the US are actually over 50 years old, and 1 in 11 bridges is rated structurally deficient. On the other hand, we have very limited resources for maintenance. The same report card puts the investment need in the US at 123 billion just to clear the backlog of all the structurally deficient bridges. Globally, the report by McKinsey estimated there is an investment need about 3.7 trillion per year just to support economic growth. However, most of the states do not have a systematic methodology for investment allocation, and usually people use worst first approach, meaning I will allocate resources for the worst bridge in my portfolio. Locally, as we can see on this slide, this is the latest report card for the state of Oregon. And here again, my focus is on bridge. The rating for Oregon bridges is at C, which is slightly lower than the national average. And the average age of Oregon's bridges is 46 years old. This is relatively old considering the fact that for most bridges, the design service life is 75 years. And we have nearly 20% of bridges at risk of becoming structurally deficient in the very near future. And at the same time, 1 in every 3 Oregonians are actually using these deficient bridges every day. So basically, in the service life of the civil infrastructure, the assets may experience gradual performance deterioration due to a number of environmental and mechanical stressors, such as corrosion and fatigue. It may also experience sudden performance drop under natural and human-induced hazard. Because of this, asset managers need to plan inspection and monitoring actions, as well as maintenance and repair actions. All these 3 aspects of infrastructure lifecycle apply to both individual structures as well as a large-scale infrastructure systems. In terms of information that can be gathered, for bridges, at least, we have a wide array of actions that can be conducted. This ranges from simple visual inspections based on human bridge inspectors. There are also more advanced technologies based on different type of sensors in the form of non-destructive evaluation, or NDE, or structural health monitoring, or SHM. The latter two has been extensively discussed by Dr. Schumacher previously in this seminar series. Based on the information gathered, the asset managers can decide whether I should post a bridge for weight limits, whether I should repair or even replace a deficient bridge. So here in this talk, I want to mainly answer three questions. The first one is, how do we quantify the economic value of information gathered from different types of inspection and monitoring actions? The second question I want to answer is, how do we make decisions based on the value of information? And finally, I want to touch something more general, that is to move from individual structures to interconnected infrastructure systems, and why this is important. So first, let's look at value of information and its quantification. The quantification of value of information in structural engineering is achieved by using structural reliability analysis and quantitative risk assessment. Structural reliability analysis for those non-structural engineers, this is basically a methodology to quantify the probability of failure given a certain limit state. And based on the probability of failure, we can combine that with failure consequence to calculate quantitatively the structural failure risk. The benefit of inspection and monitoring information is we can update our prior belief on the structural capacity and structural demand. And in this way, we can update the failure probability of the structure. And given the updated failure probability, also called posterior failure probability, we can calculate the updated failure risk or posterior failure risk of a structure. Therefore, we can define value of information as the difference between prior failure risk and posterior failure risk. Since the failure risk is usually measured in monetary terms, this value of information is also in monetary values. In the life cycle context, we can also have a different aspect of understanding value information. That is, for the inspection and SHM results we gathered from different actions, we can update of course, the current performance of the structure. But in addition to that, we can also update the entire deterioration process. The benefit of doing that is this information can facilitate decision makers for maintenance decisions. And here we can define value of information in the lifecycle context as the difference of total lifecycle cost with or without this information gathered from different types of inspection and monitoring actions. As you can see from the previous slides, a key part of quantifying value of information is to conduct Bayesian updating. And for this task, what we used is called Bayesian networks. Basically, a Bayesian network is a probabilistic graphical model to represent a group of random variables. Here, what I showed on this slide is a very, very simple Bayesian network involving 4 binary random variables. First, I have like a binary random variable representing whether it is raining outside, and another one representing whether my neighbor is washing the car, for example. And then all these 2 random variables will decide whether I can see the ground is wet outside my window. Of course, whether it is raining right now will also influence the results of weather report. The main use of Bayesian network is to conduct this statistical inference very efficiently. based on some of the information I have for the nodes in the Bayesian network. For example, back to this 4-node Bayesian network, if I see the ground is white outside my window, and if I know the weather report predicted no rain, I can update it my prior belief of whether it will be raining outside. Of course, I can I can make some decisions based on the information I gathered from certain nodes in the Bayesian network. For example, I can decide to go for a walk based on the information I have, and this decision will have a utility, meaning that I may feel better after taking a walk. If I put this so-called decision node and utility node into a Bayesian network, we call this Bayesian network an influence diagram. The purpose of doing this is we can conduct decision-making under uncertainties. So coming back to the applications in structural engineering, the Bayesian network here shown on this slide is actually for the modeling of fatigue problems in steel structures. For this type of problems, we have a number of material properties and external loads that will decide the fatigue crack propagation. And based on the fractional mechanics model, we can predict the fatigue crack sizes based on all these primary random variables. Of course, we can use inspection nodes to model different types of inspection results. The basic idea, if you can recall, is basically if I gathered some information from inspections, meaning that I have some evidence for the value of this node M1, I can update the entire fatigue propagation process, and accordingly, I can also make decisions to see whether I should repair this fatigue sensitive detail, and this repair action or repair decision will have a consequence. By comparing different inspection schedules and by comparing the life cycle cost with or without inspections, we can quantify the value of information. To give you an example of how we use Bayesian network to quantify value of information, the example here is a project we had with Office of Naval Research. What you are looking at here is a fatigue sensitive detail in a ship hull structure. And the diagram at the on the right shows the updated material properties based on the inspection results we can obtain from a liquid penetrant inspection. So we use the Bayesian network to calculate the value of information associated with different types of inspection actions, as well as different inspection results. The bar chart here shows the value of information associated with the inspection results in year 6 for different types of inspection methods. Here we considered a relatively cheap inspection method called liquid penetrant inspection, and 2 more accurate but also more expensive inspection actions called eddy current inspection and ultrasonic inspection. By using Bayesian networks, we can also answer simple decision-making questions. For example, if we didn't detect any fatigue cracks in year 6, we can answer the question that is whether we should immediately implement some additional conformative inspections. The bar chart here shows the incremental value of information given different numbers of additional inspections using different techniques. The main takeaway is for this question, if we are talking about more accurate but more expensive techniques, no follow-up is needed. If you did implement some additional inspections, this will only cost you money without giving you some extra benefit. However, if you are using a relatively cheap but less accurate inspection method, such as liquid penetrant inspection, additional inspections does provide a value of information. In fact, we can still have positive value, incremental value of information by doing up to 4 to 5 additional inspections. The second topic I want to introduce today is optimal decision making. Here I want to introduce two general genres of decision making, that is optimization-based decision making, and more recently what we call decision automation using reinforcement learning. For optimization-based decision-making, basically we have different inspection or monitoring schedules, and we can calculate the value of information or the lifecycle cost given such inspection schedules in the service life. What we want to implement is an optimization algorithm to find the best inspection schedule. Unfortunately, such optimization problem usually fall into this general category of resource constrained project scheduling problems. This means that it can be really computationally demanding. For this purpose, we used meta-heuristic algorithms such as genetic algorithms and particle swarm optimization to conduct such optimization-based decision-making. The figure here on top shows the results of such an optimization. Here you can see by using a genetic algorithm, we will be able to present the optimal timing and the best inspection techniques for a fatigue-sensitive structure. This methodology can also be used for structural health monitoring campaigns. For this purpose, we can decide when we need to start our monitoring campaign and for how long we need to have this monitoring system on the structure. Another benefit of using a genetic algorithm or a particle swarm optimization is it is relatively easy to extend from single objective optimization to multi-objective optimization. For example, we can conduct multi-objective optimization to have a set of optimal compromises between conflicting objectives such as value of information and lifecycle maintenance cost. However, we didn't stop here in terms of optimal decision making. What we want to push forward is we want to have some kind of adaptive inspection schedule and repair policies. Adaptive here means that instead of specifying when and what techniques I need to do beforehand, I want to have an inspection schedule that can update the coming inspection and repair actions based on the information I gathered previously. And I also want to automate this decision-making tools so that the decision maker can use such tools very easily. And finally, I want to answer this fundamental question, that is, if I can implement this adaptive inspection method, can I save lifecycle cost? To implement adaptive inspection planning, what I used here is to formulate this problem setting as a reinforcement learning problem. This is relatively straightforward because here we have a structure, or more likely we have a numerical representation of the structure, or the so-called digital twin of a structure. And we have a decision maker or decision-making tool. And in each year in service, the decision maker will be able to decide what type of inspection or repair actions the bridge will receive. And the structural model will provide the updated performance given the reinspection and repair actions. Of course, this inspection and repair actions will incur some kind of maintenance cost. And if we don't provide maintenance timely, there will be a tremendous failure cost. So the general idea of reinforcement learning is we want to train a decision-making tool, or so-called decision-making agent, by experiencing this feedback loop over and over again. So in the hope that at the end of the training algorithm, we will be able to have an automatic decision-making tool that can conduct adaptive inspection planning and reduce total lifecycle cost or maximize value of information. For this purpose, we developed an in-house reinforcement learning algorithm called DCMA2C. This is basically an algorithm combining deep neural networks and actor critique algorithms in the domain of reinforcement learning. I'm not going to the nut and bolts here for this algorithm, but what I want to show is this algorithm in action by showing you an application example. Here, what you are looking at is a composite steel girder bridge constructed in 2005 in Pennsylvania. What we did here is, in order to train our decision-making agent, we first translate this physical bridge into a numerical model by using finite element modeling. And what you see here is the result of using this reinforcement learning algorithm on this example bridge. And two takeaways from this slide. The first one is by using this reinforcement learning algorithm, we will be able to present a really granularized maintenance plan for each individual structural component. And the second feature of our automatic decision-making methodology is the ability to have this adaptable inspection and repair actions, as you can see in each individual plot. Basically, we don't need to specify the number of inspections anymore. We don't have to specify the repair threshold anymore. The decision-making tool can automatically make decisions based on the current and previous information gathered from previous inspection and repair actions. In terms of the benefit of using such automatic decision-making tools, we compared our methodology with more conventional inspection planning methodologies. Here, what you see is a comparison, the result of the comparison, that is, the adaptive inspection planning can reduce lifecycle cost by around 50% compared to a traditional time-based maintenance plans. And we also see that this adaptive inspection planning can reduce lifecycle cost by almost 20% compared to our optimization-based inspection planning. Therefore, we are confident that such a decision automation methodology does have a lot of potential in terms of reducing total lifecycle costs and maximizing value of information. The final topic I want to introduce today is to kind of discuss the importance of decision-making not only at the individual structural level, but also at the civil infrastructure system level. The primary reason of conducting decision-making at this network level is the fact that all our civil structures are usually interconnected in a transportation or some other type of infrastructure systems. The figure here shows a very simple transportation network from a region A to a destination B. For one of the link, we have a bridge that may fail because of structural deterioration or because of other type of hazard. So here, if we look at this problem only at the individual structural level, we will assume that only the bridge users for this bridge will be affected because of a structural failure. However, in reality, this is not the case. Because the bridge is located in a transportation network, the failure of a bridge in this network will not only affect the current bridge users, but will also propagate through this transportation network and affect the traffic users on other transportation links. This means that when we are conducting risk assessment, this consequence evaluation really should be conducted at the network level in order to really capture these network effects. To showcase what is the impact of doing this type of network level risk assessment, we conducted a study to rank bridges in the highway bridges in Los Angeles County for maintenance priorities. So here we ranked bridges for maintenance priorities based on 4 different indicators. We have first the safety rating, which is a rating developed by a Federal Highway Administration that only considers structural performance. We have sufficiency rating, which is kind of a semi-risk indicator that tries to combine structural performance with structural importance. And then we also have a bridge ranking based on structural level risk and bridge ranking based on finally network level or system level risk. To achieve this network level risk assessment, what we did here is to really take advantage of the data in various public databases. For example, for structural analysis, we used the data in a national bridge inventory to first predict structural deterioration, and second, to estimate the failure probability using a structural reliability analysis. And for consequence evaluation, as I said, this is a network level analysis. What we did here is basically to use GIS data for the area of interest and census data to get the traffic demand and network topology so that we can conduct traffic assignments to predict the traffic flow within this transportation network. By using the failure probabilities obtained from structural analysis and failure consequences obtained from traffic assignment, we can calculate the network level bridge failure risk and rank the bridges based on this network level risk. So here the slide shows the results of such a bridge ranking. The figure on the left shows the top 10 bridges for maintenance priority based on network level risk and the 2 qualitative condition and sufficiency ratings. What you can realize here is that for those qualitative or categorical indicators, it's really not able to kind of consider the bridge failure risk very accurately. You can see a lot of bridges that even though in a worse condition, but are very rarely used. On the other hand, the bridge ranking based on the network level risk can capture those structures with a really high importance that will, its failure will really impact the network level traffic performance. In terms of the structural level risk assessment and network level risk assessment, the bar chart on the right shows the top 10 bridges ranked based on these 2 indicators. So here we see that both methodologies can pinpoint similar bridges. However, for structural level analysis, it may kind of underestimate the failure risk of certain bridges, as I highlighted here in this box. In the end, what we can conclude from this study is for risk assessment of our bridge structures, even though the structures are discrete in space, it is really important to analyze the structural failure risk at the entire transportation network level. Such network level analysis is not only important for the deteriorating structures, it is also important for risk assessment under climate change, which is another aspect of my research. The slide here shows a previous study we did for Camden County, New Jersey. Here we are looking at the bridge failure risk under climate change. And again, we are using a network level approach to really analyze the network level risk under the stressor from climate change, considering different climate change scenarios. And finally, I want to mention that because of this interconnectivity of different infrastructure assets, the resource allocation really has to be conducted at the network level as well. I think this is a major difference between the resources allocation for infrastructure system to the traditional portfolio management, because here the assets are no longer independent to each other. For this purpose, we developed a risk bound method and combining risk analysis at the transportation network level and the genetic algorithm in order to have an optimal resources allocation plan for different bridges in a network. With that, I want to summarize my talk by looking at what am I positioned in this diagram from sensors to decisions. So here, my studies are mainly focused on the last two tasks for this diagram from sensors to decisions. They are data analysis and modeling and decision analysis. So what I briefly introduced today is some of my understandings between the interconnection between sensors, decisions, and civil infrastructure systems. Specifically, what I talked include this value of information quantification between sensors and structural level decisions, as well as decision optimization and decision optimization. The last part of my presentation mainly deals with the interaction between decisions and civil infrastructure systems and why the decisions should be conducted at the network level. And my future research is dedicated to really close up this loop by looking at value of information-based decision-making from not at the structural level, but at the infrastructure system level. In terms of the areas of expertise I'm looking for collaboration, first, I'm very interested in researchers doing works on Internet of Things, as well as novel data collection methodologies. Specifically, I'd love to collaborate with people doing novel NDE and SHI methods, as well as crowdsourcing data and data fusion. Another aspect that I'm interested in is the GIS-based spatial and network analysis with an emphasis on the transportation network of interdependent infrastructure systems. And in terms of the reinforcement learning part of my study, of course, I want to try different novel reinforcement learning algorithms to improve the decision-making process for civil infrastructure systems. Because once we are talking about the reinforcement learning at the network level, computational complexity becomes a topic. And finally, I'm also very interested in collaboration with people from social sciences in terms of urban planning, sociology, and economics. For this part, my idea is to really translate this lump sum failure risk into the so-called community well-being, but really consider the social disparity between different households in the area of interest. And with that, I want to conclude my presentation, and thank you very much for your attention. And I'm happy to answer your questions.
Okay, thank you, David, for a nice talk. We're gonna start the Q&A. So I see like a couple of questions from the audience. We're gonna start with Fernando. He asked two questions. The first one, I think in slide 20, maybe there is a model, finite element model. He asking about how the corrosion less related with the finite element model.
For the corrosion, basically, we assume the corrosion penetration will located at the web plate and the bottom plate, and the corrosion rate is based on the previous research. Mm-hmm. So basically, you reduce the cross-section sizes and create a new OpenSys model, and then calculate the structural performance based on this corroded structure.
Okay. The second question he asking, I think in the when you summarize your research, he said, how do you decide when and where to apply the sensors? Is there included the optimum decision process?
It could be, if you are talking about the optimization-based approach, it can be added as design variables. But for my research, for the example I provided, it was not included in the optimization problem because we are looking at fatigue-sensitive details, so we know where we are looking at. But of course, you can do that.
Yeah. Fernando, if you have a follow-up question, I can unmute you. So if you can raise your hand. So I
Yeah.
see Jel also. I'm gonna unmute you, Jel. You can ask your question, okay?
Thank you for your talk, David Yang. What types of climate change scenarios most affect the bridge failure rate?
For climate change studies, I looked at the increased temperature. This will accelerate, excuse me, this will accelerate the deterioration process. We also look at the secondary effects of climate change in terms of higher frequency and intensity of floodings. This will compromise the foundation capacity in the form of scour. And we did a sensitivity analysis, and what we found out is that this secondary effects in terms of higher hazard frequency and intensity really has a much higher role to play in terms of increasing the bridge failure probability. Does that answer your question, Jill?
Yes, is it more severe? Are the consequences more severe with high temperatures or low temperatures?
For the deterioration process, it's usually high temperature, because high temperature will have you will have like a faster corrosion rate. In terms of the hydrological events, it can be tricky, because once you have a higher temperature for certain regions in the country, you will have a lower flow discharge in the rivers. In this case, you will have a lower risk. But in some other regions, you will have a more dramatic rainfall. This will dramatically increase the flow discharge in your rivers, and this will increase your failure risk. So it's really a kind of region-specific problem.
And also, what about air quality?
For air quality, that's a good question. I think for air quality, it can be related to the structural deterioration. But we didn't look at the air quality for this purpose in terms of life cycle analysis of structures. But my guess, my kind of intuition will be it may not be as severe as hazards, like intensified and more frequent hazard in terms of for bridge safety, because what we found out that is the hazard side of the climate change impact is really more relevant to our infrastructure.
So acid rain or other chemical issues don't significantly make an effect?
It will of course have an impact, but my intuition from my study is the hazard will have a larger impact. For example, the more severe floods will have a more subsequential impact on the bridge safety.
Thank you.
Yeah.
Okay, we have another question in the chat. Chip, he asking, are you familiar with the multi-dimensional response surface model, RSM, optimization using MEPO software by Schumacher? And he mentioned specific author that has many publication or paper in this, and he said those are maybe interested for you. So.
Oh, thank you very much for the information. Yeah, I mean, for the response surface, if you're talking about response surface method, is basically one of the ways for you to kind of have like surrogate model. It's like, I think it's one of the surrogate models used to replace a more complex structural model. And so here for this specific problem, what I used for the purpose of computational surrogates is a neural network model. But thanks for the information. Of course, it's always good to try different types of model surrogating.
And I'm sorry, my bad. It wasn't a software by Schamberger. It's not by Schumacher. Okay.
Yeah, but thanks. I'd love to see more
Yeah.
about this.
I will send you the specific paper that he sent me and the author. So
Oh, that would be great. That would be great.
I'm gonna send it to you. Yeah.
Yeah, thanks.
Any other question?
I have another question.
Yeah.
I'm wondering about cavitation. When you're trying to make an automated inspection process, how do you measure cavitation? Isn't that something that needs to be done by a human?
Yes. I think the decision automation, all this decision automation is basically once I have the information, what decision I need to take, this process is automated. Instead of, I'm not saying the data gathering process is automated. It could be automated, it could be still like manual, but once I have the information gathered from this different type of inspection actions, I can have a decision-making tool to tell you when will be the next inspection, what type of inspection method you need to use, and what type of repair threshold will be relevant for your next inspection actions.
Thank you.
Yeah.
Any other question from the audience?
Yeah, I guess I can ask a more general, broader question. What do you see sort of the next thing that needs to happen that some of these models might be, some of these prediction maintenance tools might be used by decision makers? Where are we lacking? Are we lacking on having sensors on there, or what are we lacking?
I think we are lacking the communication between different researchers. For example, like what I need for my research is the probability of detection and probability of sizing of different inspection methods. But a lot of the people in sensing technologies, they don't provide such information for like downstream activities that I am doing. So I think this lack of communication and lack of focus between different group of research is the reason why this thing has not been kind of grouped together and to form like a impactful approach for like infrastructure managers.
Are these methodologies used by, if not, I see the bridge picture on right now. So are they being used right now by some DOTs, Departments of Transportation?
So this bridge example is actually the bridge drawings were provided by Penn DOT. Mm-hmm. So they are interested in actually exploring at least this type of reinforcement learning approach. But I would say the state of the practice approach is still a condition-based approach. So you kind of assign the inspection intervals and assign a repair threshold for that will trigger repair actions. But what we find out here is, so this type of conventional inspection methodologies may not give you the lowest life cycle cost. So I think people are definitely interested, but we also need to kind of push forward the boundary of research as well.
Great, thank you.
Thanks.
We have another 3 questions from the chat. So the first one, Ali, he asking you, did you apply your model to determine the remaining surface life of the bridges?
So for the for bridges, you have a design service life that is 75 years. So for that purpose, we analyzed this deterministic service life. For fatigue problems, we did predict the remaining service life based on the updated fatigue correct growth model from using Bayesian networks.
Okay, another question from they asking about how much can be the sensor, for example, the IoT and the maintenance decision built into the new bridges design and construction.
Can I say that again, please?
So he asking how much can be the sensors, for example, using IoT or and the maintenance decision built into the new bridges design and constructions.
So I think in this is we need really a shift of design methodologies to take into account the life cycle performance. For example, we can adopt a similar performance-based design approach similar to seismic design. So if we conducted such life cycle analysis, we will allow the asset owners maybe to take a lower insurance premium. With that incentives, maybe people will adopt this type of life cycle informed design more widely.
Okay, so another question from Dr. Daniel. He asking this is a kind of a diagnostic problem in a medical or a medicine. Doctor can conduct a test to diagnostic a problem, but more and more data analysis and artificial intelligence are used to predict a possible problem following by appropriate test. Here, are there a large database of tests or results on infrastructure that could also help the decision what this should be performed?
I think in terms of the data availability, we do have data from in different public databases, but the key challenge for infrastructure, especially for bridges, is usually each bridge is but it's different in its own sense. It's not like an industrialized product that can really have a lot of data for us to do like inferences. So for bridge structures, we do have some kind of condition data that is available to us, but it's really hard to have enough data to power the so-called reinforcement learning, supervised learning algorithms, and to also use Bayesian network to do inferences. So to counter that, I think to solve this question, to solve this problem, one issue we need to tackle is basically we need to have physics-based model and data-assisted, the so-called data-assisted approach that's combined the best of the two worlds. So we cannot only rely on data in civil infrastructure problems. We have to have some kind of physics-based model for us to do inferences to diagnose problems in the structures. So this is basically my understanding for the state of the art of this kind of big data problems in civil infrastructure problems.
Mm-hmm. I think the last one is Fernando. He asking about follow-up question. Go ahead, ask your question.
My question was still about the first step that will be to install sensors or not. You have identified the crack located in a specific place.
Yeah.
How do you begin? How do you identify this value at the beginning? And we need to install sensors in order to save money in the future.
For like fatigue problems, of course, you can put on your sensors based on the fatigue categories. So there are established guidelines telling you what type of fatigue details is more likely to have, what kind of structural details is more likely to have like fatigue problems. And the other approach is to really adjust your sensor kind of layout based on your information gathered from existing inspection actions. So that is like a chicken and egg problem. So I think one way is to do a localized installation of sensors, and based on your structural model to infer what would be the critical locations for the next round of inspection. By doing this incremental approach, you will be able to have the structural performance predicted and also save some of the sensors that needs to be installed on the structure.
I have another question.
Yeah.
Does this decision automation process only apply to modern bridges? If so, how modern must they be and what specific features must they have?
It doesn't have to be a modern bridges. So if you look at this this bridge model, this is like a really conventional bridge design. So the key information I need to have in order to conduct decision automation is basically, I want to have structural drawings so that I can create a digital twin or create a numerical model of a structure. Without a bridge drawing, it's relatively hard to kind of create this kind of structural model. So I think the structural model is the key. As long as I can build a structural model for a bridge, it doesn't really matter how old is this bridge. Of course, for older bridges, I may also need some condition results so that I can account for the difference between the design condition, the pristine condition, and the current condition of the bridge. But once I have the material properties, the geometric properties of the structure, I will be able to conduct such a decision automation process.
So including historical covered bridges or,
Yes.
historical
Yeah, I mean, not
structures?
really Asian structures without any drawings. That will be hard to create a model. You could do that, but it will itself involve a lot of uncertainties. Then it will cast question of how accurate is your decisions.
So I have a question.
Yeah.
So in David, in your experience, how open are departments of transportation to having those dynamic inspection schedules? I mean, do they have guidelines or even regulation that precludes them from doing this? Are they open to this? Seems like a very new way of doing work.
That's a very good question. So there is regulations in terms of visual inspection. So for example, for the bridges in the National Bridge Inventory, usually it is required to be inspected every 2 years. But for like more advanced inspection actions, for example, NDE and structural health monitoring, such regulations is more like a lenient. So because this is a more advanced technology, you will be able, the bridge owner will be able to have more control of how they want to implement that.
I think the idea of risk-based inspection has definitely been around for a while and discussed by people at the Federal Highway Administration, right? That's to not be stuck with certain fixed inspection intervals. But again, I don't know how well established that is. I think the states sort of decide how they use the inspection ratings, the condition ratings, and how they use those to, how to interpret those to make decisions. I think that's still pretty much state by state.
We have another question from the chat. Maybe this is the last question. Ali Hay asking, most of the data of the bridges inspection comes from the virtual inspection, but in some level it's not reliable. Did you consider that in your models?
So for inspection, all the inspection methods, you have two types of uncertainties that you have to consider. The first one is called probability of detection. That is, given the damage size, what is the probability actually I detect damage? And the second one is called probability of sizing, or more, some people also call it measurement error. That is, what would be the probability of having a certain measurement given the real given the value of the real damage size. So those two types of uncertainties have been considered in the analysis. This is why what I mentioned before for the question. So for the inspection management, we really need to know the quality of those inspection actions in terms of probability of detection and probability of sizing. And this is something that we need to collaborate on between people working on sensors and people working on decisions.
Okay, any other questions? Okay, Dr. Yetter, you can take the lead so for wrapping up this talk.
Yeah. Well, thank you very much, David.
Thank you for having me.
So happy that you will join us. This is a fascinating talk, and thank you for staying on the hot seat for that long. I think this is probably the longest list of questions we ever got.
Those are really nice questions. I'm really happy to answer those.
Yeah. So yeah, I think this precludes or ends today's session. If students want to hang out a little longer because they have some questions about the seminar, please do so. And for everybody else, have a very happy weekend. Thank you.
Thank you. Happy weekend.
Yeah, thanks, David, for you too. I mean,
Thank you for having
Thank you,
me.
David.
Thank you very much.
lots of opportunities ahead, just
Yeah.
listening to, what
Definitely.
it brings.
Yeah, I'm pretty excited too.
David, if you don't mind
Yeah.
to share the slides with me, maybe some student asking about the slides. If you don't mind to share the slides, you can send it to me.
Oh, sure. Yeah, I will send you the slides shortly.
Yeah, send it to me and I will distribute it to the students. So
Yeah, sure.
that.
Yeah, I'll do that.
Thank you so much.
Yeah, no problem. Should I stop sharing my screen or?
Yeah, you can stop sharing.
Okay.
Okay, yeah, I think we are wrapping up. That's it.
Okay.